I'm grateful to Christoph and Lillian Pierce for the opportunity to speak here. I'm especially pleased to be able to speak in the city in which Hausdorff worked for much of his career. So just to fix some very standard notations, the LP norm of a function will be written as f with the subscript p. I'll almost always be integrating with respect to Lebesgue measure. E with the absolute value signs will denote the Lebesgue measure of a set, and occasionally, just in some digressions, the cardinality of a finite set, but almost always the Lebesgue measure of a subset of Euclidean space. This notation is the indicator function of E. It's 1 on E and 0 on the complement of E. And I'll be talking about the Euclidean Fourier transform normalized as follows. So x is a point in Rd, c is a point in the dual group Rd, f hat of c is the integral of e to the minus 2 pi I inner product of x with c, f of x dx. Okay, and part of my slide seems to be missing. Okay, so this is, I'm afraid that means part of all the slides will be missing. We'll see what happens. The Hausdorff-Young inequality is one of the very most basic inequalities of linear analysis. So first of all, on L2 of Rd, the Fourier transform is unitary. It preserves norms. It's a contraction from L1 to L infinity. And for intermediate exponents p, if p is between 1 and 2, the Hausdorff-Young inequality says that the Fourier transform is of an LP function. The Fourier transform is in LQ, where q is the conjugate exponent, and there's an inequality. The LQ norm of f hat is less than or equal to 1 times the LP norm of f. So this was approved by Young in 1913. In this special case of even integer exponents, q is 4, 6, 8, 10, and this is a common thing in the subject. There are many theorems that have been proved first for even integer exponents, and perhaps later for general exponents, and this is one case. 10 years later, Hausdorff proved the inequality for the full range. Those were very primitive days, and if you know about interpolation, which is the method we would use nowadays to prove this in half a sentence, interpolation was simply not known back then, and Hausdorff really did not interpolate in any sense. He had a more involved argument. Okay, this inequality properly formulated works on any locally compact abelian group with a constant of 1 in the inequality, and that constant is optimal for many groups. And for many important groups, it's optimal for a torus, and it's optimal for the integers of any dimension. Okay, so my talk is about a sharp version of this inequality. The sharp version gives the optimal constant. So the norm of f hat in LQ is less than or equal to a certain constant. A depends only on the exponents. It's raised to the dimension d, a sub p to the d times the LP norm of f. And the optimal constant is, well, the AP, the optimal constant in dimension 1, is p to the 1 over p divided by q to the p to the 1 over 2p divided by q to the 1 over 2q, where p and q are the two exponents in the inequality. This was first proved by Babenko, again, for even integer exponents, by a proof which is not the one we would give probably nowadays. And it was proved for general exponents by Beckner in 1975. The formula for the optimal constants doesn't tell you very much. What tells you something about the structure in the inequality is the identity of the actual extremizing functions. So what Beckner showed is that among the extremizers of the inequality are all Gaussian functions. And in this talk, a Gaussian will always mean a complex constant times an exponential. The exponent is a quadratic polynomial. The second degree part of the exponent is negative definite and real. And the coefficient of x is allowed to be complex. So that's what a Gaussian will be. Beckner's proof shows that these functions extremize the inequality. That still left the question of whether there were other extremizers, and that was solved by Lieb in 1990. So Lieb showed that there are no other extremizers. All the extremizers are exactly the Gaussians. And along the way, he gave a completely different proof of Beckner's theorem. Whereas Beckner's proof was really very much a proof in hard analysis, Lieb's proof was a proof by symmetry. He exploited very heavily the connection between the Fourier transform in R1 and the Fourier transform in R2. If you have a product of two functions, a product function in R2, its Fourier transform is just a product of two one-dimensional Fourier transforms and things of that type. He used the rotation symmetry of the inequality, and altogether a very clever argument. So this identified the extremizers. Okay. Now this slide is just an example, but it's a very fundamental example. We all know that the Fourier transform is a non-local operator, and I just want to show some examples of how that actually plays out for this question of what the extremizers are for the inequality. So here we have the following kind of example. We take the integers 1, 2, etc., 3, up to some n. And this is a picture in one dimension. And about each of these, we put a little interval. The intervals are all of the same length. And they have a length which is 1 over some other capital M. And my function f is just the indicator function of the set E. So E is just the union of all these intervals. Okay, so E is a set of some measure. And what we want to do is we want to feed this set E into this ratio. And the fact is that if you let m or n or both go to infinity, this is bounded below uniformly for all m and n. So the interesting case is when they go to infinity. Okay? In particular, you can take, say, 100 integers, and you can take a function which concentrates in the limit as m goes to infinity and n stays fixed, concentrates equally at 100 points. And I'm not saying that those functions extremize the inequality, but they don't do a bad job. They come within a very reasonable fixed factor no matter how large m and n are. So this is a very strong kind of non-locality. There are competitors in this problem, competitors who try to extremize, that do pretty well and look nothing like Gaussians. Okay, and that will be fundamental throughout the discussion. Okay, so in my talk there's only one theorem, and the talk will mostly be about an outline of the ideas in the proof. And here's one version of the one theorem. So given a dimension, there's a positive constant c, so that for any function f in LP, the LQ norm of f hat is less than or equal to the optimal constant times the norm of f minus something concrete. So this says, of course, that, the concrete thing involves the distance from f to the set of all Gaussians. This factor G is supposed to be the set of Gaussians. This says in particular that only Gaussians can extremize, but it gives you a quantitative form of that statement. It tells you that you miss extremizing by a definite amount if you're a definite distance away from the Gaussians. Okay. Now, the exponent 2 here is, of course, optimal. If you have a function which has a maximum, then if there's any justice in the world, there are some directions in which you perturb, and it varies quadratically. So this is the best you could hope to have. But one can try to get one's hands on this other constant here. So here's a more refined version. So if f is very close to the Gaussians, in the sense that the ratio of the distance to the norm of f is very small, then there's a more concrete second term with an explicit constant here, which is half p minus 1 times 2 minus p times the optimal constant in the inequality. And then there's a little o term, which is a little smaller than quadratic. Okay, so there's a concrete statement. And you probably want me to say that this constant b is optimal, but it's not. There's a third version of the theorem which I'm going to spare you. The statement is longer and less pleasing. But in that third version, the distance is measured in a slightly different way. And in that third version, this constant b here actually appears, and it is an optimal constant. So in a sense, there is an optimal constant for this next term in the inequality. But you have to formulate it just right, and it's a little a little awkward. Okay. Now, I'm going to devote almost the entire lecture to outlining the proof of a much weaker statement. So this is a completely non-quantitative statement. So again, factor G is a set of all Gaussians, which is a certain finite dimensional subvariety of LP of RD. And this theorem says that given any epsilon, there exists a delta, so that if you come within a factor of 1 minus delta of extremizing, then you must be within distance epsilon of a Gaussian with the appropriate homogeneity in the norm of F. Okay? Not just the statement, but the proof itself give absolutely no information about the dependence of delta on epsilon. There's a compactness step which loses all information. Okay. So in fact, this is the main step. Even though I'm aiming for a very precise theorem, the main step is this very imprecise one. Okay. This really is a compactness statement of the following type. Suppose you have a sequence of functions fn whose norms approach 1, so that the norm of the Fourier transform approaches the optimal constant. So that's an extremizing sequence. Then what you want to say is such a sequence must be precompact. It must have a convergent subsequence. Okay. As I'll show you in a minute, this inequality has an enormous non-compact group of symmetries. So this can't possibly be true. For instance, you could take an actual Gaussian and just translate it more, and it would run off to infinity. So you'll have to bring it back. The precise statement here is that if you act on each function by an appropriate element of the symmetry group, which I'll explain in a minute, then you get a set which is precompact that has a convergent subsequence. Okay. Now, the theorem I stated in the last slide said that you have to be close to, if you nearly extremize, you're close to a Gaussian. What this version proves is that extremizers exist, and if you nearly extremize, then you're close to an extremizer. So Lieb identified the extremizers as Gaussians, and the theorem epsilon that I stated is a combination of the compactness statement and the theorem of Lieb. Okay, so the theorem of Lieb is very much a part of the story here. Okay, so the proof of the theorem goes like this. There are really 3 parts. There's this compactness statement, which shows that near extremizers, after renormalization by symmetries, form a precompact set. That lets you take limits. One invokes Lieb's theorem to identify the limits as Gaussians. And then there's a third step, which is completely different in technique. Once you know you're very close to an extremizer, you can take the functional norm of f hat over norm of fp. You know f is very close to a Gaussian, and you expand this in Taylor series about a Gaussian, and you just analyze the quadratic part of that Taylor expansion. So that's rather algebraic. I'll talk a little bit about that at the end, but that's not the main point. So that's how one goes from a completely non-quantitative statement to a rather precise one. It's because at the end you can do a completely different analysis once you know you're close to a Gaussian. Okay. All right. So the inequality has a number of symmetries of various kinds. And a very important one is you can compose a function with any element of the general linear group, and the ratio of the norms is completely preserved. Okay? We're accustomed in analysis to seeing inequalities that are invariant under translation, maybe rotation, often dilation. It's rather rare to have the full affine group as a group of symmetries, but one has it here. Okay. One has translations. One has modulation. One can multiply f by an arbitrary unitary character. And of course, one can multiply by scalars. So as a result, there's a big group of symmetries that's certainly a non-compact group, and that has to be taken into account in any sort of precompactness argument. Okay. The presence of the affine group as a group of symmetries, of course, strongly suggests some of the things that might arise in the analysis, namely things that are invariant under affine transformation. So, of course, the class of convex sets is affine invariant. The class of ellipsoids is affine invariant. And, of course, we expect to see ellipsoids. Those are super-level sets of Gaussians. Okay? And, of course, well, that suggests what you might see, but there are other things that are invariant under affine transformations as well. So those are what I call continuum multi-progressions. So first of all, discrete multi-progression is a well-known kind of object. So it's a set Q. It has a starting point U. There are finitely many steps, V sub I, and you're allowed to step a certain prescribed number of times in each direction, V sub I. And all sums that you can get to in that way with a certain number of steps in each direction, that's a multi-progression. All right, so here I gave you, well, let me come to this in a second. What we're going to be working with are continuum multi-progressions. They are sums of discrete multi-progressions and ellipsoids, or if you prefer, convex sets, either one. Those are equivalent definitions for my purposes. So a continuum multi-progression is the sum, all the points you can get by adding elements of a discrete progression to a convex set. So in one dimension, the convex set or the ellipsoid is just an interval, and here we have a typical example of a continuum multi-progression. Here's the discrete part, and then this is the continuum part. Okay? And of course, those are invariant under affine transformations. Okay. An important concept in the proof will be quasi-extremizers. So if you have a number delta, which typically will be very small, a delta quasi-extremizer of an inequality like this is a function f for which the norm of t of f is greater than or equal to delta times the optimal constant times the norm of f. So we're mainly going to be interested in the case where delta is very close to 1, but the proof has to use the case where delta is very small. Okay, so those are quasi-extremizers. And for many inequalities, it's interesting to study quasi-extremizers. It's a rare inequality for which you expect to be able to find optimal constants and extremizers exactly, but quasi-extremizers are more robust. They tell you a lot about the inequality, and that's something that's interesting to characterize. One expects to be able to do that more often than actually finding extremizers. Okay, we're going to exploit a connection with Young's convolution inequality, and indeed, Hausdorff's original proof of the Hausdorff-Young inequality did this. He used the fact that a square is the Fourier transform of a convolution, and he used Poincarel's theorem. He used other known cases of the inequality, and he was able to reduce to facts about convolution that had been proved by Young. So Young's convolution inequality, I've specialized the exponents a little, says that a certain LR norm of a convolution of two functions is less than or equal to a constant times the LS, the product of the LS norms, if R and S are related by a certain a scaling relation. Okay. The optimal constants in this inequality are known, the extremizers are known. One knows that if the only way to nearly extremize the inequality is to be near an extremizer. So this is something that's already well understood from the point of view of today's talk. So here's the lemma. If you have a delta, and if f is a delta quasi-extremizer for the Hausdorff-Young inequality, then it's also a delta quasi-extreme, then a power of f is a delta quasi-extremizer for Young's inequality with appropriate exponents. You have to change delta to delta squared, but that isn't so important for me. Okay, so the point here is that quasi-extremizers of one inequality are closely related to quasi-extremizers of the other. And that will allow us to extract information about the Fourier transform inequality from information about the convolution inequality. The convolution inequality should be much easier because there's no cancellation involved, at least if I put in absolute values. So that's a more elementary kind of inequality. Okay, now sharp constants for the two inequalities are not connected in this way. There are certain cases where you can go from one to the other, but for the full range of exponents, it's not the case that you can connect near extremizers for one to near extremizers for the other in a simple way. Okay, Young's inequality is really about sumsets, and this is where the additive combinatorics starts to come in. So the sum of two sets, A and B, is just a set of all pairwise sums, little a plus little b, where little a and little b are drawn from the two sets. And we think of non-negative functions as just being sets with weights. The function is a weight on its support. And the convolution of two functions is just a count of, it's a kind of weighted sumset, the convolution of f and g at some point x is just the number of ways of writing x as an element of the support of f plus an element of the support of g, weighted by the weights f and the weights g. So you weight each pair by the product of a value of f and a value of g. Okay, so it's reasonable to expect that some sets may appear in our discussion at least for Young's inequality, and therefore they should be around for the discussion of Hausdorff-Young. Okay, now I told you that it was going to be important to understand quasi-extremizers for the Hausdorff-Young inequality, and I said they were related to quasi-extremizers for Young's inequality. So here we characterize quasi-extremizers for Young's inequality. So suppose that f is a delta quasi-extremizer in this sense. Then you can decompose f into a structured part and a part that's smaller than f itself. So f is g plus h, where the two summands have disjoint supports. The norm of h is smaller than that of f by a definite amount. The norm of h is less than or equal to a constant strictly less than 1 times the norm of f. And the structured part g okay, sorry. There we go. The structured part g is supported on one of our continuum multi-progressions. It satisfies, it's an L infinity function which satisfies a natural bound on the L infinity norm that gives you the right upper bound on the LP norm. So that bound depends on the measure of the set. And the multi-progression, and this is a crucial point, the rank of the multi-progression, the number of different directions in which you're allowed to step, is controlled by a constant that depends only on the quality, depends only on the delta in the quasi-extremizing condition. Okay? So you get a part which may only be a small fraction of the norm of f, but it's a definite fraction, and that part is very much connected to one of these continuum multi-progressions. And then you get a part whose norm is strictly less than the norm of f by a definite amount. Okay. So those are quasi-extremizers for Young's inequality, and I just want to tell you a little bit about what goes into understanding that. It's connected to inverse forms of the Brun-Minkowski inequality. Now, the Brun-Minkowski inequality is really an inequality in dimensions greater than 1. So what I'm stating here is the one-dimensional version, which is a very simple thing, is not really the Brun-Minkowski inequality at all, but that's the part that's really relevant. So Brun-Minkowski inequalities give lower bounds for measures of sumsets. And for Borel subsets of the real line, the Brun-Minkowski inequality, the one-dimensional one, says the measure of a sumset is greater than or equal to the sum of the measures. Okay? Now, of course, it can be much larger. We know that if you add two Cantor sets which are appropriately constructed, they can each have measure 0, and yet the sum can fill out a whole interval. So there's certainly no upper bound on the measure of a sumset in terms of the measures of the summands. But there is this nice lower bound. Equality is attained for intervals. If you add two intervals, the lengths are the measures, and the lengths obviously add. And equality is not attained in any other cases except when you modify by null sets. Okay, so that's the one-dimensional Brun-Minkowski inequality. And what we need are what we ultimately want to know is a characterization of when we're close to equality here. So that situation is addressed by two classic theorems of Freman, which date back to the 1950s. So I'll call the first one, which I think is the better known one, I'll call this Freman's big theorem. This is the classic version. So A and B now temporarily are finite sets. So think of integers. So we have finite sets of comparable cardinalities. So if the measure of the sum set is less than or equal to k times the measure of one set, remember it's got to be at least twice. If the sets are equal, it has to be at least twice. So if it's less than or equal to k times the measure of A, then A is contained in a multi-progression. You get control of the cardinality of the multi-progression, and it's a natural control. It's proportional to the size of A. And there's an upper bound for the rank of the multi-progression that depends only on k. Okay. This is actually the main tool that I'm going to be using. And I'm going to need it actually in the regime where k is arbitrarily large. You would think that I would need it only in the regime where k is like 2 plus a little bit, but in fact we need it for large values of k. For large values of k, the right dependence on k is not known. They're quantitative bounds, but they're perhaps not optimal, but those issues won't come in. I just need some sort of version, and the way that things depend on k is unimportant to me. Only the fact that they depend only on k will matter. Okay, then there's Freman's little theorem. So suppose that you have a finite subset of z to the d, or of z. Suppose that A plus itself has a cardinality a little less than 3 times the cardinality of A. So remember, it's always at least twice, or at least twice the cardinality minus 1. So here we're within a factor of 3/2 of optimality. And if that happens, then A is contained in a progression of rank 1. So a discrete thing with only one step. And moreover, you get a bound for the cardinality of that progression, which is absolutely tight. It's exactly what you expect from looking at simple examples. Okay? So that is Freman's little theorem. That's in the spirit of the kind of theorem I'm telling you about today. It's a theorem that addresses the case of when you're very close to optimizing. In this case, minimizing. Okay. Now, it's a very easy exercise to pass to the limit and to convert these to theorems that work for Lebesgue measure. Lebesgue measure in Euclidean space for the first one, Lebesgue measure on the real line for the second one. And so one can use these in the continuum as well. That's not a problem. Okay. Now, over the last couple of years, I've written a whole series of papers which applied Freman's little theorem, the one about being close to optimality in one dimension, to various inequalities that are affine invariant, for which extremizers were known, and the theorems have characterized near extremizers. So these inequalities are Young's inequality for convolution, the Brun-Minkowski inequality in arbitrary dimensions. A more quantitative form of this was done by Figali and Jerison using the same ideas subsequently. And the Ries-Sobolev inequality, which says that if you convolve two functions and integrate against a third, that's less than or equal to what happens if you symmetrize the three functions radially about the origin. Okay. But I have not found a way to apply this little theorem of Freman to the Fourier transform. And so what I'm going to explain now is a method that uses the big theorem, the rather imprecise but very, very general one, in its place. Okay. And of course, symmetrization inequalities, rearrangement inequalities don't work well with the Fourier transform because cancellation's involved. It's global. It doesn't seem to work. Okay. So here's a statement for Young's convolution inequality. So if you take two sets which have positive finite Lebesgue measures, and if the convolution of their indicator functions is as large as possible up to a factor of delta, then those sets are connected to continuum multiprogressions. So there exists a continuum multiprogression whose measure is appropriately controlled. So the intersection of that progression with the set A has reasonably large measure proportional to the size of A itself. And the rank of the multiprogression is bounded above by a constant that depends only on delta. Okay? So what this gives you is it gives you the fact that a certain part of A has structure. Namely, roughly, it looks like one of these continuum multiprogressions. That's the kind of statement we want for quasi-extremizers. Okay. Now, I told you about Freman's theorem. Freman's theorem gives you control if you know a bound for the entire sumset. Here, you don't know a bound for the size of the entire sumset, but what you do know is if a sumset of two sets is small, then many elements of the sumset can be represented as sums in many ways. Here, the assumption is essentially just the latter, that many elements of the sumset can be represented as sums in many ways. And there's another theorem of combinatorics which I'm suppressing, the Balog-Semeretti theorem, which bridges the gap between the hypothesis here and the hypothesis in Freman's theorem, where you know that the entire sumset is controlled. So I'm going to omit that from this talk, but this is another bit of combinatorics that needs to be used here. Okay. So now we're going to need a couple general facts about operators. These have nothing to do with the Fourier transform. This is just something about bounded linear operators. So T is a bounded linear operator from LP to LQ. And suppose that you have a function f which is a near extremizer for the inequality. Suppose you take that f and you split it in two parts with disjoint subparts. If phi is a part which has a norm which is bounded below by a constant times the norm of f, then phi need not be a near extremizer, but it has to at least be a quasi extremizer. So the norm of T of phi is bounded below by a power of the quality eta times the norm of phi. The principle here is if you have a team that's trying to achieve some goal, everybody in the team has to contribute. It's wasteful if part of the team contributes nothing. Okay? The second part says that the team has to work together towards a common goal. So if you decompose f as a sum of phi and psi, and if both phi and psi have norms that are bounded below by a constant times the norm of f, if you multiply T of phi times T of psi and take the LQ over 2 norm, as you should, then that again is bounded below in an appropriate way. So this says if you split the function in two, if they both have a reasonable size, then those two parts have to work together to make T of f large. Okay, so those are very reasonable things and they're very elementary to prove. Okay. Here is a preliminary statement about the structure of functions that nearly extremize the Hausdorff-Young inequality. So we're given that f is a near extremizer. Norm of f hat is greater than or equal to 1 minus delta times the maximum possible. Let epsilon be greater than 0, and then if f is close enough to extremizing, then you can decompose f as before. So f is the sum of two parts with disjoint supports. Associated to this, there's one of these continuum multi-progressions. One part we don't know much about, but it has very small norm, as small as we want relative to the norm of f. And the other part has structure. So G is supported on this multi-progression. G satisfies an appropriate L infinity type bound, and the rank of the multi-progression is bounded above by something that depends only on epsilon. Okay? Suppose for a minute you had an actual extremizer. It's a Gaussian. I want to capture a Gaussian in one of these continuum multi-progressions. Okay? I can't do it. The best you can do is to take a very large ball, and then you capture almost all of the mass of the Gaussian, and a little bit is left out. So in that example, the unstructured part would be the part of the function near infinity. The progression would just be the ball, and G would be the part of the Gaussian that lives inside the ball. Okay? But in general, the theorem doesn't give us that kind of picture. It also gives us a discrete part to the multi-progression, and the rank of that discrete part is controlled, but that's all we know about it. It could be extremely sparse. Okay. So the way you prove this is we know about quasi-extremizers. So you apply that lemma, and you split f as a part that has some structure and a part whose norm is slightly smaller than the norm of f. The part that's slightly smaller than the norm of f either has negligible norm or it has pretty big norm, in which case it's a quasi-extremizer. So you split it as another part that has structure plus something with yet smaller norm, and you just do this over and over again until almost no norm is left. You get a sum with an enormous number of terms. Each one has its own continuum multi-progression. And that's not the statement here. My statement has only a single multi-progression, so there's an extra step missing where you prove that all those multi-progressions are in fact compatible, and their union is contained in a single multi-progression whose size and rank are still controlled. Okay? So that comes from the principle that all parts have to work together. All right. So there's a number of steps here. Okay? So this part just says what I just said to you orally. You just take a little bit at a time off and you keep going. Okay. So this gets us to a decisive juncture. We now know that any near extremizer looks roughly, very roughly, like this picture. You have this continuum multi-progression, you have some sort of L infinity bound, you have a little bit of norm left over. The main thing you don't know is that this thing could potentially have a discrete part, and this discrete part could potentially have rather high rank. So what we want to do is we want to replace this picture by a picture which looks more like this, a single interval or convex set. And that is really the decisive step of the proof. So I haven't given any hint yet about how that is done. Okay. So before I explain to you that decisive step, I'm just going to skip ahead and tell you about the other steps in the proof that come after it. Okay, and then we'll go back to the main step. So the next thing that happens is a stroke of real good fortune. All the people in the audience who are specialists in partial differential equations know that when you prove a pre-compactness argument, there are essentially two things you need to rule out. You need to rule out mass going off to infinity, either by your function spreading out too much or by being translated. Okay, and that roughly is what I've done with this first part of the proof. Of course, it does, in a sense, go off to infinity, so I haven't really done it, but at least I've got some kind of geometric control. But you also need the same thing for the Fourier transform. And the methods I've explained are all really working with positive objects. They don't seem to apply very well to the Fourier transform. So this inequality is self-dual. If f is a near extremizer, then a power of f hat, this is f hat times absolute value of f hat to the q minus 2, that is also an extremizer. And therefore, anything I have successfully proved about all near extremizers f applies with powers to their Fourier transforms as well. Okay? So I now know for free that the Fourier transform of f also looks like this picture, although it could be a completely different looking continuum multi-progression, but at least there's a continuum multi-progression for f hat as well. Okay, so that's really good. And then there are a bunch of smaller steps. You get, so remember, the decisive step says you can replace this picture by a single convex set. We have that for f, we have that for f hat. You have to prove that you're near the bounds, the limit provided by the uncertainty principle. So you need to prove that the product of the measures of the convex set for f and the convex set for f hat, the product is bounded above by some constant. Okay. Then you prove that they have compatible geometry. So you prove that one is contained in the polar of the other up to some dilate. So not only do they look like convex sets, but they really look similar. And then by using the symmetries of the inequality, you can replace each of them by using John's theorem. You can replace each of them by a ball. And you can make the balls have radii essentially comparable to 1. Okay? So now we have a lot of control on the geometry. Now, as I said, even if you have a Gaussian, you may need to take a very large ball if you want to control almost all of the LP norm. So these two balls can be rather large. The product of the measures is bounded above by something that depends on how much of the mass you want to capture. Okay. And for the experts, there's a tiny hitch at the end. What you end up what you want to show the Fourier transform doesn't have mass near infinity. So you want to say that high frequencies contribute little to the LP norm of f. What this argument actually proves is that high frequencies contribute little to the LQ norm of f hat, and the Hausdorff-Young inequality doesn't go backwards, so you can't control f. So it turns out that by a little bit of functional analysis, just using the strict uniform convexity of the unit ball of LP, you can go backwards if you're dealing with near extremizers. So putting all this together proves the compactness theorem completely once one can do that decisive step, and the decisive step was to get rid of the discrete part. Okay? Okay, so that's what remains to be done. It all comes down to this. Okay, so here is a digression to the case of discrete groups. You can ask the same question about the Hausdorff-Young inequality for the integers or another discrete group. The optimal constant then is 1 for all exponents. It's a much simpler situation. Among the extremizers are functions supported on a single point, and in fact those are the only extremizers. And the theorem characterizes near optimality. So if f is a near extremizer, then there exists a single point where nearly all the LP norm of f lives. Okay? So near extremizers are supported on almost on single points. So this was first proved by Eisner and Tao, and independently a bit later by Sharpened and myself, by somewhat different arguments. There's a paper of Fourier from the 1970s that comes rather close to proving this sort of thing, and Eisner and Tao used Fournier's method. Sharpened and I relied on the discrete form of the Brunn-Minkowski inequality, the lower bound for the measure of a sumset. And so that was the main tool for us. So in any case, if you have a discrete group, the only way to nearly extremize is to be supported on a single point. Okay? To be nearly supported on a single point. So I want to emphasize this because this will be absolutely decisive in the proof. Okay. All right. We need a little bit of a geometric fact. What we have so far is our function lives on one of these continuum multi-progressions with very high rank, arbitrarily high rank. I want to tame that a little bit, and here's a lemma which says that any multi-progression of controlled rank in Euclidean space actually looks in a certain sense like the integers. So we're given here, this is the torus, the quotient space. This norm is the distance from x to the nearest integer. You're given a progression P in Rd. It has some controlled rank R, and its Lebesgue measure is 1. And you're given an arbitrarily small constant delta. And then you can map this progression by an affine automorphism so that the image lies within delta of the integers. And of course, you can do that just by multiplying by a very small constant. But there's a constraint. The affine mapping, its linear part, has a Jacobian determinant which is bounded below by an appropriate power of delta. Okay? So that prevents you from cheating too much and mapping everything close to the integers. Okay? So this is a little, the form of this is maybe seems a little strange, but a typical example is if you have equally spaced intervals like this, where the lengths are epsilon, and the spacing is 1 over epsilon, and the spacing is square root of epsilon, and the number then would be what? The number would be like epsilon to the minus a half. I guess I need epsilon to the minus 1 of these. How about that? Okay. If you want to map this and you want to put each of these near the integers, you can't expand it too far, because this interval expands into an interval. If you make it too big, it can't stay near the integers. There's a constraint that you don't collapse things too much. And in a case like this, it's pretty clear the optimal thing to do is to dilate by a factor of epsilon to the minus a half. So that converts the spacing to a unit spacing and puts you near the integers. Okay, so that's maybe the simplest example to bear in mind, but the lemma is completely general. Okay? Now, I'm not saying that z to the d is actually a good approximation. If you start off with a progression of very high rank and you look at the image very near an integer, you will see microstructure. You'll see something whose rank has been reduced by the dimension, but you'll still see very much this multi-progression structure. Okay? So it's not it's a very weak kind of approximation. Okay? And when you do this, you destroy a natural normalization in the problem. You no longer have a lower bound on the measure of the image set. You might have to use something with very large Jacobian determinant, as is clearly essential in this example. Okay. All right. Okay, so I'm going to skip over that slide. And so what we need to do now is to prove that if we have a near extremizer for the Hausdorff-Young inequality, if it's supported very close to, say, the integers, then in fact it's supported very close to a single integer. And again, that's just a restatement of the somewhat simplified form of the decisive step. Okay? So we want to prove that we don't look like this, but that we look like just like one little part. Okay. And so the idea here, very much like Lieb's analysis, is to play with the connection between the Fourier transform and different groups. So in particular, what I want to do is I want to regard, say we're in dimension 1, I want to regard the real line as being nearly isomorphic to the product group of the real line with the integers. Okay? So if you have a function that's supported very close in the integers, well, there's this mapping from the product space down to the real line. X comma n goes to x plus n. That's not an isomorphism. But if you work with x's that are very close to 0, then you don't see that it's not an isomorphism until you sum things together many, many, many times. So this is an example of a Freman isomorphism of very high order. And it's in that sense that R cross Z is going to be nearly isomorphic to R. Okay, so what I'm going to do is I'm going to exploit a Fourier transform version of this algebraic fact. Okay, and to do that, we need to use, actually, there are 5 Fourier transforms that come into this discussion. I've only listed 4 of them. So don't worry too much about the notation. There's a Fourier transform for RD. There's a Fourier transform for ZD. There's a partial Fourier transform on the product space where you take the Fourier transform only with respect to the discrete coordinate, leaving the continuum coordinate alone. And there's a genuine Fourier transform on the product space. And all these are related in various ways. Okay, and now we're going to take our problem on R, let's say, and lift it up to the product space, R cross Z. And it's best to think about this pictorially. So what you have is, at this juncture, if the dimension is 1, you have a function that's supported very near the integers. So it lives on a union of very short intervals like this. And what you should imagine is taking each of these intervals and rotating it so it's perpendicular to the blackboard and turning it into a whole line. So you get a picture with a bunch of parallel lines, and so you get a picture of the product of the integers with the real line. And what we do is we take our function on each interval and we just paste it onto this rotated interval in the most obvious way. So that's my lifting. Okay, so now I have a function on the product group. And a very simple lemma says if you start on R with a function which nearly extremizes the inequality, then the lifted function still nearly extremizes the inequality. Okay? This just uses the fact that if a function has very small support, its Fourier transform varies very slowly. What we've done is we've added an extra coordinate in the Fourier space, but our function has a Fourier transform that's almost independent of the new coordinate. And so we don't really change norms much at all. Okay. Now you can get the Fourier transform in a product space by first taking a Fourier transform with one coordinate and then taking a Fourier transform with respect to the other. We do the discrete coordinate first, and we have to nearly extremize that inequality. So now, for each x, for each distance from the blackboard, the function on the integers in the transverse direction is a near extremizer for the discrete problem. And those have been characterized. So the conclusion is that my function is supported near a single element of this integer lattice. Okay. Now there I've cheated. The argument I showed you actually shows you that for each slice parallel to the blackboard, it's supported for the most part at a single point. I still have to prove that all those points match up and really give you a single point, and I'll leave that step out. That's not one of the deeper steps. Okay. All right, so this is just a heuristic justification that I already said, and that concludes the proof of the compactness theorem. Okay? So at this point, one knows that if you nearly extremize the inequality, you have to be close to a Gaussian. But because there's a compactness step, it's impossible to extract any sort of quantitative information from this proof. So now one wants to make it quantitative, and that's the last part. All right, well, I already explained what you want to do is you want to take this function and you want to take a second order Taylor expansion about an extremizer that is about a Gaussian. And there's immediately some bad news. There's a complication that comes not from the Fourier transform, but rather embarrassingly from the LP norm. That is not in any sense a twice continuously differentiable function. Because Gaussians can be very small, you have to do a Taylor expansion about a value that's near 0, and the function t goes to t to the p is not c2 if p is less than 2. So there's actually a problem here. Okay, so here's a general lemma about this sort of thing. One has a bounded linear operator from LP to LQ, any bounded linear operator. We have the assumption, though, that p is less than 2 and q is greater than 2. So that's special. Okay, suppose you have an extremizer, capital G. We're going to do a perturbation about that. So we're going to take that and we're going to add a small amount to it, and we're going to feed it into the ratio of norms. Okay, So the lemma says that for any perturbation, which is in a suitable sense transverse to the tangent space to the manifold of extremizers, that's all we need to look at. For any such perturbation, there's a splitting so that the ratio behaves in the following way. You get the leading order term, the value at the point you're perturbing off of. You get the formal Hessian matrix of second derivatives, but evaluated only at a part of the function f that you're perturbing by. And then you get a term which is unfortunately enormous, but fortunately has a favorable sign. It's controlled by the LP norm of the distance to the set of extremizers. That would completely beat out the quadratic bound I'm trying to prove, but this is a negative perturbation, so it makes the functional smaller. It works in my favor. And then there's a very small quadratic part. Okay, so this is a general lemma, which just has to do with the fact that the exponent p is less than 2 and q is greater than or equal to. So the upshot is you can pretend your functional is twice continuously differentiable, even though it's not. And all that's left is to analyze this main term, the quadratic part of the formal Taylor expansion. Well, if you work this out, this becomes an eigenvalue problem for a specific self-adjoint compact linear operator on L2 of Rd. And that operator is take a function, multiply by a certain Gaussian, convolve with a second Gaussian, and multiply again by the first Gaussian. Okay? And this, with the right values of S and T, is what's known as the Mailer kernel or the Mailer operator, and everything about it is known, so you get all of its eigenvalues. Okay? It turns out that in dimension 1, if you're going to analyze this problem for real value functions in dimension 1, what you need is the fourth eigenvalue to be strictly less than a certain threshold. This has to do with the fact that the manifold of Gaussians real Gaussians is three-dimensional. So the fourth eigenvalue comes in naturally, and it turns out the third eigenvalue is equal to the threshold. The fourth eigenvalue is less, and so you get the theorem. Okay, so that's the end of the story. Thank you.
Which of course is not an LP for any P. But it looks like you're fighting this as an enemy when you look at these, you know, it's a formal eigenfunction, so Fourier transform applied to it is itself. It's not, doesn't have any LP norm. It has a value still, right? And the value is 1, I guess, of your normalization.
Right, so notice it doesn't actually quite extremize. It gives you a constant of 1, not any of the constants strictly less than 1. So it actually beats the function. Yeah. So what you're trying to Yeah. So what you're trying to do is you would imagine taking that example and cutting it off. That would make a competitor. And the question is, how well can you do by cutting it off? And the theorem says, no matter how you cut it, you cannot come close to extremizing the inequality. That's one corollary.
Well, it sounds like that's exactly what you were aiming at when you were drawing the picture.
Right. So roughly, the way you should think about that is if you take this infinite sum of Dirac masses, think of that as a progression of rank 1, multiply it by a Gaussian, you're now really introducing, in some sense, a second, you're making something of rank 2. That's the way to think of it. And of course, rank 2 is not optimal. That's why nothing like that works, essentially because it's a rank 2 construction.